All right, we're going to just continue with the Laplace transform and see what's going on with this. We defined the Laplace transform of f to be the integral as t goes from 0 to infinity of f of t times e to the minus st dt. And it's important to recognize this is a function of s, and this thing may not exist. If it exists, then it's our lucky day and we're happy. Okay. And we found that the Laplace transform of t to the n is n factorial over s to the n plus 1. And we have the Laplace transform of the sum of two functions is the Laplace transform of the first one plus the Laplace transform of the second. And the Laplace transform of a constant times f, I can pull that constant out and just focus on f. We are now going to build up our library. So what we're going to do is we're going to kind of just build up a library of functions. And we know this. It would be nice if we know some other things. Well, since we're solving differential equations, we know that exponentials are important. So let's play with that. So by definition, it's going to be the integral from 0 to infinity of e to the at, that's our function, times e to the minus st dt. And I can bring these exponents together because I'm multiplying two exponential functions with the same base. And let me factor out a t, and notice I'm integrating with respect to t. So this becomes the limit as m goes to infinity of the integral from 0 to m, e to the minus st dt. Now I can use the fundamental theorem. So the limit as m gets big, I'm going to have what? 1 over a minus s e to the a minus st from 0 to m. I can plug in these bounds. So I got 1 over a minus s times e to the a minus s times m minus 1 over a minus s. And now I get e to the a minus s times 0. So let's see. I got to be very careful here now. This is only going to converge only if a minus s is negative, which means that s has to be bigger than a. Okay, so if s is bigger than a, then this term goes to 0. I'm going to get minus 1 over a minus s. E to the 0 is just 1. And by convention, we usually write it as 1 over s minus a. And the reason we do that is that it just makes things a little cleaner when we start doing partial fractions later. Okay, so we now have the Laplace transform of t to the n is n factorial over s to the n plus 1. Laplace transform of e to the at is 1 over s minus a, with the caveat that s has to be bigger than a. So, for example, Laplace transform of e to the 3t is going to be, so in this case a is 3, so I get 1 over s minus 3. If I look at the Laplace transform of e to the minus 3t, in this case a is minus 3, so this becomes s minus 3, so I get 1 over s plus 3. And again, if I want to take the Laplace transform of e to the minus 2t, a is minus 2, so I get 1 over s plus 2. And if I know that the Laplace transform of some function is 1 over s plus 2, I can write this as 1 over s minus a minus 2. This is now looks like 1 over s minus a, where my a is minus 2. So I know that my g of t is e to the minus 2t. So if I know the Laplace transform of h is 1 over s plus 8, I can write this as 1 over s minus a minus 8, which means now my a is minus 8. So my h of t is going to be e to the minus 8t.